Good evening. Welcome to the RSES Technical Webinar Series. I'm Sean Lundeen, RSES Senior Customer Service Representative. I'd like to welcome everyone to tonight's webinar titled TEV Operation, Installation, and Troubleshooting, presented by Adam Keith. If you don't know Adam, he started his career as an applications engineer in the industrial refrigeration industry, working primarily with ammonia refrigerant. As an applications engineer, Adam's expertise consisted of valve sizing, selection, and technical support. Adam then transitioned into a sales role in industrial refrigeration before moving to the commercial side of the refrigeration industry. He is currently a sales engineer for Sporlan, covering the Chicago territory. Tonight's presentation will last approximately 45 minutes, and afterward, there will be a Q&A session. Please submit any questions that you have throughout the presentation using the GoToWebinar dialog box on the right-hand side of your screen. We'll be fielding those questions to our speaker tonight, so give them some good ones. This presentation is being recorded and will be available for online viewing at your convenience as soon as possible. Now I'd like to introduce you to our presenter, Adam Keith.
All right, let me get this shared here. And let's see, screen. All right, Sean, how's it look? Can you see just the slide?
Yeah, it looks fine.
All right, so want to thank you all for joining us today, and I appreciate the introduction, Sean. As Sean mentioned, today's topic is going to be TEV operation, installation, and troubleshooting. All right, so yep, if you guys can do me a favor, as Sean mentioned, and type any questions that you have into the chat section, that'd be great. At the end, Sean's going to give us an opportunity to answer as many of those questions as possible. Okay, so here's the link to our website, www.sporlan.com. And if you scroll down on that main site, in the top left, you'll see a section called HVACR Training and Learning. And you can find a whole bunch of different webinars that our engineering team put together during the pandemic on a variety of different valves. So use that in your free time if you want on a different valve that you have interest of learning in. On the bottom right, you'll see a section called Literature, Bulletins, and More. And then when you click on that, there at the top is Thermostatic Expansion Valves. I'm going to be covering a lot of the literature that you'd see under this section here. So I just wanted to point this out so that you can use it as a refresher if you forget certain topics that we discussed today. All right, now here is the agenda today. So it's all about the TEV, otherwise known as the Thermostatic Expansion Valve. So we're going to be covering the following topics. We're going to talk about what is the function of the TEV in the system. We're going to give you a breakdown of the internal components. We'll talk about the principles of operation, and then we will go through variations of different TEVs that Sporlan offers, and we'll finish it up with some installation and then troubleshooting tips to help you solve some problems that arise as a technician. Okay. All right, so this is one of the most important slides in the entire presentation, so make sure you pay special attention to this one. As you can see, the TEV resides at the interface between the high pressure and low pressure sides of the system, and its function is to keep the evaporator as fully active as possible without overfeeding it. The way that it does that is by controlling the superheat at the outlet of the evaporator. In the bottom left, I've listed some of the common misconceptions of what the TEV does, because in the opinion of Sporlan, it is probably one of the most misunderstood components in the entire system. So it does not control temperature, it does not control suction pressure, and it does not control humidity. Going back to the picture on the right, I want to point out that the TEV is just one of several different options that you would have as a metering device, or an expansion device, I should say. Systems such as your basic household refrigerator probably has something as simple as a capillary tube, but today's presentation is entirely about the TEV. All right, so what is superheat? As heat is applied to a saturated vapor, superheat is created. So superheat is the temperature of the refrigerant vapor above its saturation temperature. And the TEV is going to modulate in response to a change in the superheat in order to maintain the superheat at its setting. You probably also noticed on this slide that I'm pointing that it alludes to the three fundamental pressures that are necessary for the TEV to control superheat. So this is just a little bit of a teaser because we're going to discuss those three fundamental pressures in a little bit. All right, so now that you know that the TEV is controlling superheat, why do you need superheat? So the first part is for load management. Having the right amount of superheat is going to help you optimize the performance of the evaporator. You're going to need to have the proper amount of superheat in order to manage the heat load and keep the space or the product at the temperature that you're trying to maintain. Underfeeding the evaporator would result in you underutilizing the effective surface of the evaporator and getting less cooling capacity out of your system than the system was designed for. So that's point number one. The other reason you need superheat is to protect the compressor and to avoid flood back. So I look at superheat as an insurance policy. By having some superheat, you're ensuring that you're sending vapor back to the compressor and not liquid. Because sending liquid or having continuous flood back will wash away the lubricant from the compressor and result in premature wear or damage. All right, as a technician, you're going to be need to be able to calculate superheat, especially for troubleshooting purposes. In order to calculate superheat, you're going to measure the suction line temperature near the sensing bulb. You'll then resort to a gauge to find the evaporator pressure, and you will correspond or correlate that evaporator pressure to a PT chart to find the saturation temperature in that evaporator. By taking the difference between the suction line temperature and the saturated temperature in the evaporator, that's what we're referring to as superheat. So I showed you a few slides ago where to find the literature on our website. What I want to point out is that we have a form called 10-135 under the educational material section, and it's titled Using PT Analysis as a Service Tool. So wanted you to let you know that that's there so you can refer back to it at your convenience. Also notice the pressure tap in the picture. So it is customary on a refrigeration system to have the pressure tap at the outlet of the evaporator, but on an air conditioning system, you'll pretty much always have the pressure tap at the condensing unit. So got our first poll question here.
The first poll question is, what is the function of the TEV in a refrigeration or HVAC system? A, control superheat at the outlet of the evaporator. B, control evaporator temperature. C, control relative humidity in the space we are trying to cool. Or D, control evaporator pressure. Let's see. All right, I'm going to close it here in about a few seconds. All right. All right, so for the first poll question, which was, what is the function of the TEV in a refrigeration or HVAC system? Actually, 99% got this right and chose A, control superheat at the outlet of the evaporator, and only 1% chose control evaporator pressure. And, now back to you, Adam.
Okay. Oops, look like I might need to, bear with me 1 second here. I gotta minimize this again. Okay, there we go. Okay. All right. So looking at the internal components now of the TEV. So this is going to help you when we get into the principles of operation. It's going to tie everything together here. So there is a dashed boxed line around the thermostatic element, which consists of the sensing bulb, the capillary tube, and the diaphragm. And I do want to point out the fact that nearly all Sporlan TEVs do have a thermostatic element that is replaceable in the field. So when looking at the thermostatic element, it does have a selective charge inside of it that's completely isolated from the system refrigerant. And the charge is the main factor in determining what type of application, meaning what system refrigerant and what saturation temperature in the evaporator that particular TEV is going to be used for. But we'll discuss that point here in a few slides. Moving clockwise down to the bottom right, you have an adjustment assembly on the valve. If you remove that seal cap, you'll find a adjustment stem, and that is how the technician can change the superheat setting of the valve. So the adjustment stem does not control the capacity of the TEV. That is also a very common misconception. Speaking more on the topic of capacity, from a mechanical standpoint, there is three things that control determine the capacity of the TEV. That is the diameter of the port, the stroke of the push rods, and the angle of the pin. So I also want to point out the fact that the pin is actually below the port on a TEV. So moving further clockwise around, you've got a removable strainer that's depicted on this particular TEV. Not every Sporlan TEV has one of those, but the TEVs that we sell for refrigeration and supermarket applications typically do, because it's far easier to clean the removable strainer than it is to clean the valve. So our EG, SBF, SBQ, and SR models are the variations of the TEV that have that removable strainer on it. And I'm going to tie that point together nicely when we get into the troubleshooting, because it's going to relate back to the fact about removing contaminants from the system. All right. If I had to say, the next 4 slides are probably the most important 4 slides in the entire presentation. So on the previous slide, I referred to the 3 fundamental pressures that allow the TEV to control superheat at the outlet of the evaporator. So I'm going to go into more details here on this now. So your 3 fundamental pressures are your bulb pressure, evaporator pressure, and your spring pressure. And the equation states that the bulb pressure has to equal the evaporator pressure plus the spring pressure. If I was to reword that, you would say the opening force has to equal the sum of the closing forces. So I've depicted the bulb pressure as labeled as number 1 here in the picture on the right-hand side. And you can see that it's acting down on the top side of the diaphragm, and it's trying to drive the TEV further open. Your evaporator pressure is labeled as number 2, and your spring pressure as number 3. And both of those are closing forces. I want you to see that they are acting on the bottom side of the diaphragm, and they're directly opposing the bulb pressure. They're trying to drive the valve further closed. So I've mentioned already that the technician can change the superheat setting of the valve by using the adjustment stem on the bottom. And the reason that works is because using the adjustment stem actually changes the preload on that closing spring. And the spring pressure is going to be essentially constant once that valve has been adjusted to the desired superheat setting. So going back to bulb pressure, the next question is what creates bulb pressure? I've already mentioned that there is a thermostatic charge inside the thermostatic element, and the charge is really what makes the magic of the valve happen, if you will. The bulb of the thermostatic element is going to be connected to the suction line, and that bulb temperature should match the temperature of the refrigerant vapor at the bulb location. When that bulb temperature increases, the pressure inside the thermostatic element also increases, creates more force or pressure on the top side of that diaphragm. It flexes the diaphragm, causing the pin to move away from the port, allowing more flow through the valve and into the evaporator. So the valve is going to continue in this opening direction until that bulb pressure balances with the sum of the evaporator pressure and the spring pressure. And the position of the pin in relation to the port is going to be determined by that difference between the opening and closing forces. All right, so now that we've kind of broke that down, I want to show you a real example that's going to really kind of tie this all together here on the operation of it and how it controls superheat. So in this example, we've got a R410A refrigerant. We've got a balanced load. And so we have a 40-degree evaporator temp. That's our saturation temperature inside the evaporator, which is very common for an air conditioning system. Looking at the PT card for R410A, you'd see that a 40-degree evaporator corresponds to 119 pound evaporator pressure, which is acting on the bottom side of the diaphragm. Again, this is just an example, but in this example, we have a bulb temperature of 50 degrees, which means our superheat is 10 degrees Fahrenheit. And I've got a little equation in the bottom right-hand corner of the slide that shows you how I came up with that 10-degree superheat. So if you take your 50-degree bulb temp, you subtract your 40-degree saturation temp in the evaporator, that gives you that 10-degree superheat. So as you recall, the bulb temp, or bulb pressure, sorry, is an opening force, and it's dependent on that temperature. A 50-degree bulb temp, if you look at R410A PT card, is about 143 pounds of opening force acting down on the top side of that diaphragm. So your spring pressure in this case is 24 pounds. Remember that you could, as a technician, you could adjust that adjustment mechanism and change that spring pressure to change the superheat setting. But we've got 10-degree superheat here. We happen to have 24 pounds of spring pressure. So the sum of our closing forces, which is our 24-pound spring pressure and our 119-pound evaporator pressure, gives you 143 pounds of closing force. And we've got 143 pounds of opening force. So these forces balance, and the pin is not in motion either away from the port or closer to the port. What we say is that the valve is balanced load feeding. It is feeding, but it's balanced load feeding. It's not in motion. All right. So if we have an increase in the heat load, we want to see how the TEV responds in order to maintain that 10-degree superheat setting that we had the valve set to on the previous slide. So example I have, this is an air conditioning system. We've got a room temp that we're trying to maintain at 70 degrees. Let's say 10 more people walk into the room and the heat load increases. How does the TEV now respond? So the first thing I want you to notice is that the point of complete vaporization moves closer to the inlet of the coil. So the point of complete vaporization is where all of that liquid has boiled off into a vapor. When you move that point of complete vaporization closer to the inlet of the coil, you now have more effective evaporator surface area in which the refrigerant vapor can pick up superheat before the sensing bulb. So in this case, instead of a 50-degree bulb temp, the bulb temp went up to 55 degrees Fahrenheit. And if you look at your PT card, a 55-degree bulb temp for an R410A system would give you about 156 pounds of opening force on the top side of the diaphragm. So let's see. All right, notice also that the spring pressure is still 24 pounds. Unless the technician goes up and adjusts the stem, you're not changing the spring pressure. We've still got 119 pounds of evaporator pressure. So our total closing forces are still 143 pounds. but we've got 156 pounds of opening force. So the TEV the pin is going to go farther away from the port. It's going to let more liquid into the evaporator until you bring that superheat setting back down to the 10-degree setting that we had under the balanced load conditions. So let's look at the opposite example now, where you have a decrease in the heat load. So same system, let's say 70-degree room, and 5 people leave the room, so the heat load goes down. How does the TEV now modulate in order to maintain that 10-degree superheat setting that it was set to? So as the heat load decreases, that point of complete vaporization is actually going to move deeper to the outlet of the coil, leaving less evaporator surface area for that vapor to pick up superheat before the bulb. So instead of a 50-degree bulb, which we had under the balance condition, bulb temp went down to 46 degrees, and we only have 6 degrees of superheat now. Again, I'll refer back to that equation in the bottom right. The 46-degree bulb temp minus the saturation temp of 40 degrees is how I came up with that 6 degrees of superheat. So a 46-degree bulb temp now gives us 133 pounds of opening force on the top side of the diaphragm, and neither our spring pressure or our evaporator pressure have changed. So we still have 143 pounds of closing force and only 133 pounds of opening force. So the valve is going to respond by having the pin go closer to the port, let less liquid through the valve and less liquid into the evaporator until we have increased that superheat setting, or increased the superheat back up to the 10-degree setting that we had that at. So final point is that this is somewhat of a extreme example, if you will, because I want to make sure it's clear that the valve is going to be constantly modulating. It's not waiting until the superheat deviates by 4 or 5 degrees away from the setting before it starts to modulate. It's constantly modulating to maintain that superheat at the desired setting. And then I guess final point I want to make on this slide here is that this is a major benefit of using a TEV as opposed to a fixed orifice or a capillary tube, which don't have the ability to maintain superheat with a change in the heat load in the space. All right, moving on to the charge in the thermostatic element here. So it is critical to have the correct thermostatic charge for the application that the TEV is being used in. The biggest factors determining the element selection are the temperature that you're having the evaporator and the system refrigerant. Sporlan does believe in using selective charges, and here are a few of the charges that we offer. So your GA charge, this is your air conditioning charge. This C charge, I think, is commercial refrigeration. That's how I think of it as, which is used in applications having a evaporator temperature between 0 degrees and 40 degrees Fahrenheit. The Z charge is low temp, so I think of it as walk-in freezer, for instance. And you would use the Z charge in an application that has an evaporator temp between 0 degrees and negative 40 degrees Fahrenheit. I typically like to use an analogy of the thermostatic charge being somewhat similar to hydraulics, in which you need to have a proper amount of liquid present in the element under the entire range of operating conditions that you're going to see. So we'll tie this together under the troubleshooting, but having an improper thermostatic charge for the application is definitely going to result in inconsistent or unsatisfactory superheat control, even if you have that valve sized properly. So even if the valve is properly sized for the capacity, it is still not going to effectively control superheat if you've got that wrong charge relative to the application you're trying to use it on. And again, we'll go into that more under the troubleshooting piece. So far, we spent a lot of time discussing the fundamental pressures, one of which was the evaporator pressure. And when we are discussing internal versus externally equalized TEVs, really what we're saying is, how does that evaporator pressure make it to the underside of the diaphragm to act as that closing force? So starting on the left, what does it mean if we have an internally equalized TEV? Well, internally equalized TEVs actually sense the evaporator pressure at the inlet of the evaporator, and they bring in that pressure through an internal passageway in the valve body to the underside of the diaphragm. And they only have two connections on them. If you have an externally equalized TEV, it has a third connection, which is typically a 1/4 inch or an 1/8 inch. It's a smaller connection, and it would be connected to the suction line downstream of the sensing bulb. So pressure, you're taking the pressure from the outlet of the evaporator, you're letting it through that third connection on the TEV, and that's where it's sampling that pressure to the underside of the diaphragm. I want to mention that a externally equalized TEV can always be used to replace an internally equalized version of the same valve, and you won't experience any negative repercussions in terms of system performance. So I do understand the fact that installing a third connection on a system that didn't have on it originally is a bit of an inconvenience for a technician. But as far as system performance, you won't experience any negative repercussions from using a externally equalized TEV in place of an internal. But the opposite is not true, and I'll show you that here on the next slide, actually. So next question you're probably asking is, when is an externally equalized TEV required in order to have proper system operation? And what I would say to that is, if you have a distributor on your evaporator, you're definitely going to need an external equalizer. For the most part, you're really only going to see your internally equalized TEVs on your really small self-contained systems, like maybe a 1/2 ton or a 1/4 ton reach-in cooler that you might see in like a gas station or a convenience store. All right, so here's kind of this is going to tie in nicely to troubleshooting, but I'm going to show you here, if you misapply an internally equalized TEV and put it on a system that really should have a externally equalized one, here's what's going to happen. That's what I'm going to show you on this slide here. So many evaporator designs have significant pressure drop through the actual coil itself. And then certainly if you have a system that has a distributor, it's essential for the distributor to have a significant amount of pressure drop across it, or you're not going to have good distribution of liquid to all the circuits of your evaporator. So in this example, we've got a 55-pound suction pressure R404A system, and we said we've got 20 pounds of pressure drop through the coil in this example. So if you look at the top left of the slide, our pressure at the inlet of the evaporator is 75 pounds, and that is the pressure that an internally equalized valve is sensing on the underside of the diaphragm, because it's going up through that internal passageway that we talked about on the previous slide. So the end result now, because that evaporator pressure is a closing force, and if you go through the 3 fundamental pressures that we talked about on the previous slide, it happens to be the case in this example that the superheat is going to be 23 degrees. And that is way too high of a superheat, so you're actually going to starve this coil. So that prompts me to the next slide of how much superheat is the correct amount of superheat relative to the application. So the table that I'm showing on the picture here can be found in our quick tips booklets that we hand out to our Sporlan authorized wholesalers. So you don't necessarily have to ingrain this to memory if you remember that you can find this in the quick tips books. But regardless, we do recommend that original equipment manufacturers that have certain guidelines around what superheat they want to see on their particular piece of equipment, that is highly recommended to follow that OEM guideline. But if you do not have guidelines from the OEM, you can refer to our general guidelines here. And the way we came up with these guidelines is it's really all based on the temperature differential, or the TD, which is the difference between the saturation temp of the coil and the ambient air temp in the space we're trying to cool. So the higher the TD, the higher the suggested superheat setting is going to be. On an air conditioning or heat pump system, which has a TD in excess of 20 degrees Fahrenheit, which can exist, we recommend a general or a superheat setting in a range of 8 to 12 degrees. Moving down to a commercial refrigeration application, so think your walk-in cooler here, which has a lower TD, usually in the range of 10 to 15 degrees. We require a slightly lower superheat of 6 to 8 degrees Fahrenheit. And then getting down into our lowest temperature application, which would be your walk-in freezer, for instance, many or most of those applications have TDs of 10 degrees or lower, which is why we suggest a superheat setting in the range of 4 to 6 degrees Fahrenheit. But remember, if the OEM has guidelines, follow their guidelines. Okay, got poll question number 2 here, Sean.
All right, poll question number 2. An internally equalized TEV can always be replaced with an externally equalized TEV, and system performance won't be negatively impacted. Option A is true and option B is false. I'm going to close it in a few seconds. And so the question was, an internally equalized TEV can always be replaced with an externally equalized TEV, and system performance won't be negatively impacted. 82% got it correct and chose option A, which was true, and 18% chose option B, which was false. And now back to you, Adam.
All right, so this is a really good example of a installation that we saw in real life that ties in nicely to making sure you use a internally or externally equalized TEV in the correct application, and it ties in nicely to the installation here. So this was a environmental chamber, and the customer complaint was that the hot gas bypass valve was overfeeding. And so they even went as far as saying that the environmental chamber had not worked properly in the 6 years or so since it had been started up. So we visited the site, and what we found was that the real issue was not that the hot gas bypass valve was overfeeding, it was that the TEV was underfeeding. And so what I want to point out is that if you look, that this is an externally equalized TEV, but they installed that external equalizer at the inlet of the distributor, and it was not installed at the outlet of the evaporator on the suction line. So also there was another issue on this system. If you look on the right side, there's another TEV that is feeding a dehumidification coil. I'm going to show you on the next slide the issue we found there. So here's the dehumidification coil, and you're going to notice how long that coil is, which means there is a substantial amount of pressure drop through that coil. So the customer installed an internally equalized TEV on this feeding this dehumidification coil, but they really should have installed an externally equalized TEV instead. So the result here was that they had poor dehumidification because they were starving that dehumidification coil by using an internally equalized TEV. All right, moving on to balanced port versus conventional. So you've likely heard those terms when talking about TEVs. Earlier, I described to you that there was 3 fundamental pressures that ultimately control superheat at the outlet of the evaporator. But we've ignored a 4th pressure that sometimes can interfere with that process. So if you look at the picture on the left there, you've got your high pressure liquid from your condenser coming in the inlet, and that liquid pressure actually pushes down on the top side of the pin and creates a fourth force that is trying to tell the TEV what to do. It's trying to influence it to open. When you have systems that have a high side pressure or a condensing pressure that change throughout the operating season, which is very, very typical, you end up with a variance in that fourth pressure as it attempts to change, or as it changes and attempts to drive that valve to a more open position. So the end result is that in some instances, the TEV can starve, it can flood, and that's all dependent on the ambient in which the superheat setting was set. So basic takeaway, we created the balance port to get around that. And what I want you to notice here is that on the picture on the right, this is a balance port design, and it has an integral pin and push rod assembly with a shoulder machined on the top side of the push rod. So the upper shoulder and the lower pin surface have a similar area, which actually neutralizes the opening influence of that liquid pressure. So what I'm saying here, if you look at that picture there, your liquid coming into the valve is going to be pushing up on that shoulder, which is attempting to close the valve with the same amount of force that it's attempting to push down on the top side of that pin. So you've basically, you've neutralized that fourth pressure that we talked about, or that fourth force. So I am highly recommending the use of a balance ported TEV over a conventional port. All right, getting into the installation of the bulb and the external equalizer, I definitely need to stress how important proper installation is. And so starting with the sensing bulb, where possible, the bulb should be connected to a horizontal, free draining section of the suction line close to the evaporator outlet. And so it should not be exposed to an airstream within the fixture. And you definitely want to make sure that you tighten down the bulb strap or the bulb with the appropriate bulb straps that we supply with every TEV that we sell. We've seen customers that use zip ties or duct tape, and that is highly not recommended because the duct tape or the zip ties are not going to hold up properly under freeze thaw conditions, nor are they going to give you a really snug connection with the bulb and the suction line. Talking about the orientation of the sensing bulb now around the circumference of the suction line, you want it to be installed at 4 o'clock or 8 o'clock on the suction line. And now talking about the external equalizer. The equalizer should be piped to the top of the suction line just downstream of the sensing bulb. So we've been asked numerous times why or what negative repercussions might happen if you install the external equalizer on the upstream side of the sensing bulb. And the answer to that is you could get a small amount of liquid that influences the bulb temperature if it travels down the equalizer line. So that's why you always install the equalizer downstream of the sensing bulb. All right, also talking about bulb location here, you want to be mindful of interference with the fittings. So the entire bulb needs to be in intimate contact with the suction line. Looking at the picture on the right side, you can see that the bulb has been installed on top of a bushing. So you can actually see daylight between part of that sensing bulb and the suction line. That is not correct. Picture on the left is correct, which you're using the appropriate bulb straps, and it's not installed on any type of bushing, and it is on the evaporator side of the P-trap. All right, now what I'm trying to show you in this slide is that the placement of the fastener or the bulb strap, the straps is important when you're looking at the installation. So on the picture on the right, you can see that for the position, that bulb strap to be positioned such as you might end up crushing the bulb if you don't install it right. So picture on the left is how we want to do that. All right, poll question number 3, Sean.
All right. Where should the external equalizer be connected when using an externally equalized TEV? Option A, it shouldn't be connected. You can cap off the external equalizer. Option B, just downstream of the sensing bulb. Option C, just upstream of the sensing bulb. And option D, as far as possible from the outlet of the evaporator. All right, I'm going to close it in a few seconds. All right, so the question was, where should the external equalizer be connected when using an externally equalized TEV? 1% chose option A, which is it shouldn't be connected. You can cap off the external equalizer. 91% chose the correct answer, which was just downstream of the sensing bulb. 7% chose option C, which is just upstream of the sensing bulb. And no one chose option D, which was as far as possible from the outlet of the evaporator. And now back to you, Adam.
Great. Okay. Well, lost my, bear with me 1 second here. Oh, lost it. Let's see. Sorry, give me 1 second here. Had a minor exit out of this here, and then.
No problem.
All right. Is it good? Is it good? Can you see poll question number 3?
Yeah, I can still see poll question 3.
Okay. Now I just moved it to the next slide. So
yeah, it advanced.
Okay. So adjusting superheat now. So superheat can be adjusted on TEVs that have an adjustment assembly. So first, you're going to remove the seal cap. Some valves that Sporlan makes do have a packing gland, and that would be the G valve, the S valve, and the O valve. And so the majority of refrigeration valves that we sell TEVs for refrigeration applications do not contain a packing gland. But for the ones that do, you can loosen that packing nut using a Sporlan superheat wrench shown in the middle picture there. And those wrenches are handed out readily to our Sporlan authorized wholesalers. After you get that packing nut loose, you will adjust the stem a quarter to a half turn at a time. And turning that clockwise increases the superheat. Turning counterclockwise decreases the superheat. Point number 4 is very important. So after you make that adjustment, the quarter to a half turn at a time, you need to let that system settle out. So you need to give it 15 or 20 minutes before making any sort of further adjustments. We get technicians who make an adjustment 5 minutes after they've already adjusted it. And really what they do is end up chasing their tail here because the system has not had time to settle out appropriately. Final step is to tighten that packing nut and put on the seal cap. And I want to make sure you know that it is important to put that seal cap back on because the seal cap has a knife edge seal and it is constituting the final seal there. All right, here what I'm showing you is a side-by-side of a non-adjustable versus an adjustable TEV. We do sell some non-adjustable TEVs to our original equipment manufacturers. And what I'm trying to show you here is that even in the event that you walk up to a non-adjustable TEV, we offer parts kits that can be used to convert a non-adjustable TEV over to an adjustable one. Bulletin 1 is our replacements part catalog, and that's what we need kits to make that conversion. All right, getting into troubleshooting now. So to begin the troubleshooting process, you need to know the high and the low side system pressures and what refrigerant is in the system. Those are the basics. And beyond that, you really should measure your superheat, as we showed you on a previous slide. And you should also figure out how much subcooling you have at the inlet of the TEV. So once you have got all those measurements and you understand those operating conditions, then you're in a position where you can begin to troubleshoot. A couple things that can go wrong with a TEV is that it can starve the evaporator, which would show up in the form of high superheat and low suction pressure. It can overfeed the evaporator, which would show up as low superheat and high suction pressure. And then the final thing is that it can hunt, which is excessive modulation. All right. Reason I'm showing you this PT card here is because on the next bunch of slides, we're going to go under the go through the different bullet points or different checks that can cause the symptoms we were referring on the previous slide, such as high superheat or low superheat. But I'm showing you this PT card because we hand these PT cards out to our Sporlan authorized wholesalers. And in addition to having the saturation temperatures bottom section as a basic checklist or a refresher of the different troubleshooting pieces that we're going to talk about on the next slides. So use that as a refresher if you remember it's there. All right, so there are many reasons for high superheat. You can have contamination in the system, which would show up in the form of moisture, dirt, or wax. You can have high superheat adjustment. You can have charge migration, which is applicable to MOP style charges. We have not talked about MOP charges. Point number 4, you can have a dead thermostatic element, which means the charge has been drained from the thermostatic element. You could have the wrong thermostatic charge, which we've already touched on. You could have no external equalizer, meaning you have an internal equalized valve in an application that should require an external equalized one. You could also have a capped equalizer, which we've seen, right? If it has that third connection for the external equalizer, it has to be connected. We've seen instances where the contractor or the technician has capped that off, and that's absolutely problematic. Bullet point number 9, we've got a low refrigerant charge. You can have flashing at the TEV inlet, which would be indicative of no subcooling, and that greatly takes away from the capacity of the TEV. And then finally, you could have low pressure drop across the TEV. Kind of a rule of thumb that we say is you need about 50 or 60 pounds minimum of pressure drop across that TEV in order for it to work properly. And then the 12th thing is you could have an undersized TEV. So sticking with point number 12, I want to mention that on our website, we have Virtual Engineer, which is free for all of you. And you can quickly go in and use it to confirm TEV sizing for either a new install, or you could even check the sizing of a problematic TEV in the field to see if it is a sizing issue. All right, identifying a dead element. So the dead element is when the charge has drained out of the element. So if you suspect you have a dead element, you can increase the bulb temperature by holding that bulb in your hand, and then you will look for changes in the suction temperature or the pressure. The thermostatic element can be removed once the TEV has been isolated from the system refrigerant pressure. And there's a buffer plate that you'll find in the bottom. If you're able to push that buffer plate in or deflect it with your fingers or thumb, it's basically a sure sign that you have a dead element. All right, moving to low superheat and high suction pressure, which is the result of overfeeding the evaporator. An overfed evaporator would typically experience low superheat and could even experience that liquid flood back to the compressor. So on a conventional system, which is one evaporator and one compressor, you would typically see high suction pressure when you have low superheat. On a rack system that has an EPR, you would not necessarily see high suction pressure in addition to having that low superheat. But here are the possible causes of low superheat. Would be TEV seat leakage, low superheat adjustment, bulb installation, which is poor thermal contact on the bulb, having the wrong thermostatic charge, another contamination issue in the form of moisture, dirt, or wax, having an incorrect external equalizer location. The example that we've used as installing that external equalizer downstream of an EPR, which is not correct. You could also have a oversized TEV or have a issue with the compressor where it's getting low capacity. Moving on to hunting. Hunting arises when you have big swings in superheat. So I do want to mention that moderate or a small amount of hunting is acceptable, but severe hunting can cause flood back to the compressor and can cause control issues with the TEV. Potential causes would be low load, having an oversized TEV, air logging, poor airflow, or having poor refrigerant distribution. So we'll show you here on the next couple slides, we'll touch on that distributor, but having an oversized distributor nozzle will definitely cause TEV hunting, or it certainly can, I should say. So elaborating on the second bullet point, which is the oversized TEV, I want to mention that a balanced port TEV can operate effectively down to 25% of rated capacity and still control the superheat. What I'm saying here is that a 4-ton TEV could effectively control superheat at a 1-ton load. So I am not suggesting that you install a 4-ton valve on a 1-ton system. I'm merely saying that it can effectively, if the load drops off and your load drops down to 1 ton, a 4-ton balanced port TEV could still effectively control that superheat. So I want to mention that when checking TEV sizing, it is very important to consider both the maximum load and the minimum load. So a lot of technicians make the mistake of only considering the rated evaporator capacity when they're checking TEV size, and that's a mistake. You definitely want to consider the minimum load condition as well. All right, poll question number 4.
All right. What are the benefits of a balanced port TEV over conventional port? It prevents floating system head pressure from causing inconsistent superheat control. A balanced port TEV can control superheat down to 25% rated capacity. And C, conventional port TEV can control superheat down to 35% of rated capacity, or option D, all the above. All right, I'm gonna leave it open for a few more seconds. All right, so the question was, what are the benefits of a balanced port TEV over conventional port? It prevents floating system head pressure from causing inconsistent superheat control. Option B, a balanced port TEV can control superheat down to 25% of rated capacity. Or option C, a conventional port TEV can control superheat down to 35% of rated capacity. Or option D, all the above. 23% chose option A, 29% chose option B, 1% chose option C, and 41% chose option D, which was a correct answer, all of the above. And now back to you, Adam.
Okay, let's see here. Sorry, we got to minimize this again here. All right. All right, so now touching on the distributor, I really want to mention that it is critical for TEV operation that you have good distributor performance and a correctly sized distributor. So what is the purpose of the distributor? It's to provide a good mixture of liquid and vapor to each circuit of the evaporator. And so having a oversized distributor nozzle causes poor liquid distribution. So you get overfeeding of one circuit of the evaporator and underfeeding of other circuits of the evaporator. Proper sizing of that distributor is in getting enough pressure drop across that distributor is critical to get enough velocity where you have good mixing of the liquid and vapor so that you get proper distribution of liquid to each circuit. All right, here we go. Okay, so the distributor size matters. I mentioned this slightly in the previous slide, but if you have poor distribution causes circuits to starve and other circuits to be overfed, and the result of that is that the TEV is prone to hunting, which can cause a flood back to the compressor. So I've already mentioned back earlier in the presentation that pressure drop across the distributor, you need substantial pressure drop across it. And that is why you need a externally equalized TEV anytime you have an evaporator that has a distributor on it. For systems deploying capacity control for compressors, the distributor nozzle and tube combination should be checked for both maximum and minimum load conditions. And you also want to note the impact that liquid subcooling can have on the distributor size. So I mentioned Virtual Engineer that you can check it for TEVs, but you can also use Virtual Engineer to size your distributors or check a distributor that is already installed out in the field and find out if it's appropriately sized. All right, final thing is the contamination. So I mentioned that system contamination can have very negative implications on system performance. We offer the catch-all, which is intended to remove contamination from the system and protect the system components. So what we say at Sporlan is that anything besides refrigerant and lubricant in the system is considered a contaminant. And I also want to point out that another thing we say is that the TEV is the second best filter in the entire system. And as you all know, you do not want your TEV to get plugged up because it's acting as a filter. So that's why it is critical to get your contaminants out of the system. All right, one of the last slides here is another installation issue. This TEV was actually installed backwards. You can see the strainer, which is the inlet of the TEV, is actually installed on the outlet of the valve here on the distributor side. So that strainer is not protecting any contaminants from plugging up the TEV. Reminder that our website is at sporlan.com. And here I've put my contact information. So I am in the Chicago territory, which is really most of Indiana and Illinois. If you're in that territory, please do reach out to me for any technical questions. Outside of the Chicago territory, we have 60 sales engineers in North America and Mexico, and you should contact them for any technical questions. But if you don't know your local sales engineer, you can contact headquarters at the below phone number and email. And then we do have YouTube channels and a Facebook page and Twitter page where you can stay up to date with what's going on at Sporlan. I think it's time now, Sean, to open this up to any questions if we have a few more minutes.
Yeah, we have a couple minutes here. Let me see. There's a couple good questions that came up. I know you talked about not capping the equalizer, but what would happen if the equalizer bin was capped?
All right, good question. So remember that equalizer or the evaporator pressure is actually a closing force on the valve. So the initial reaction to a capped equalizer, since you've lost that closing force, would be for the valve to go wide open. Right. That's what would happen initially. but then you might see eventually that the valve actually goes closed after a certain amount of time. If you get any sort of small traces of refrigerant that would leak past the push rods or something like that, you'd build up enough pressure to actually close the valve.
All right, and then where that one? There was another going. Oh, can the seat/needle wear out on a TV over many years of use?
I have not really heard of the. Well, we do leak test or seat test our TEVs before they leave, but I have not really heard of wear on the seat being an issue. But what I would like to do is I will circle back with you, Sean, and give you more appropriate answer on that.
Awesome, thank you. And then got another one here. With AC working in low ambient temperature with low ambient kit dose, does it affect the TV operation? I could read that.
So, yeah, read that one more time, Sean.
With AC working in low ambient temperature with low ambient kits, does it affect the TV operation?
So if you have good head pressure control, that is one of the reasons that it's critical to have good head pressure control, is because if your head pressure falls too low, you actually lose capacity out of your TEV because you don't have as much differential pressure across the port. So does that answer your question? Having good head pressure control is critical for the performance of the TEV. Whether we're talking about air conditioning or refrigeration, that's true in both scenarios.
All right, and thank you. And then another question here, can TEV work with all oils and have no issues?
Yes. Yep, we have not. So any of your common refrigeration oils should not have any sort of negative impact on your TEV if it's a accepted refrigeration oil.
Awesome. And then I'll do one more. It's a shorter one. It's interesting to me. What is the gray or black sludge found in a TEV?
So that, you know what, that may be, I'm going to go out on a limb here, that may be like copper oxide, which if you don't braze, if you don't run nitrogen when you are brazing, you end up with this like scale on the inside of the system. That's one of the reasons it's very important to run nitrogen when you're brazing.
Perfect. And then all the other questions I will log and get over to you. And if anyone has questions, they could email me afterwards, and I will get it over to Adam to get the proper answers out to you guys. And now I just wanted to show you how to view the webinars. The screen comes up again. Okay. So I think everyone can see my screen now. I just wanted to thank you, Adam, again, and for everyone attending the webinar tonight and for presenting the topic. For those of you who would like to view this presentation at a later date, you can do so in the next few days on the members only section of rses.org, which I can show you how to get to right now. So once you get to rses.org, you're gonna click join now, or not join now. You're gonna click sign in at the top of the screen, and then enter your login credentials here below. And sorry about that. And then hit the orange homepage thing at the top left of your screen, and hover over training, and you could go down to webinar archives, and it will be there tomorrow morning sometime. And then also, if you would like to view this at a later date and still receive CEHs, we will have it on our learning management system, which is going to be launched here shortly. And I also wanted to mention that webinar attendees from tonight's live event will receive a certificate for completing 1 hour of continuing education about 1 day after this event ends. And once again, if you have any questions for me or Adam, you can email me at webinars@rses.org. Again, that's webinars@rses.org. Thank you again, everyone, and have a great day. This webinar is now concluded.
Thank you, Sean.
Thank you, Adam.